Welcome to Stochastic Processes. Today we are exploring the pure birth process, a fascinating mathematical model used to understand systems that only ever grow, like viral videos spreading on the internet or bacterial colonies multiplying in a lab. Imagine a stadium filling up for a concert where the exit doors are locked. People can enter, but absolutely no one can leave. This is the intuition behind a pure birth process. It is a stochastic process where the state, representing the population size, can only increase by 1 or stay the same. The rate at which new arrivals happen is called the birth rate, denoted by lambda sub n. Because it has that subscript n, it means the speed at which new arrivals happen can change depending on how many individuals are already in the system. Now that we understand the basic idea, let us visualize it. Here you see a state transition diagram. Each circle represents the number of individuals currently in the system. The arrows show the one-way path from one state to the next. Notice how the arrows are labeled with lambda 0, lambda 1, and so on. This shows that the probability of moving to the next state depends entirely on the current state you are in. There are no backward arrows because departures are physically impossible. This visual model translates into a fundamental differential equation. This equation tells us how the probability of being in state n changes over time. It loses probability when a birth occurs, pushing the system to the next state above it, which is represented by the negative term. At the same time, it gains probability when a birth happens in the state just below it, moving the system up into state n, which is represented by the positive term. This balance dictates the flow of probability. This brings us to a simpler version of the equation for the starting state. If we are looking at the very first state, usually state 0, there is no state below it to transition from. Therefore, the equation drops the second term entirely. This tells us that the probability of staying in the starting state only ever decreases over time. As time goes on, births will eventually happen, pushing the system out of state 0 forever. The negative sign perfectly captures this continuous loss of probability. Before we see how these equations are derived, let us use the starting state formula in a real scenario. Consider a computer network that starts completely empty. New users arrive at a constant rate of 4 per minute. We want to find the exact probability that the network remains completely empty after half a minute. We start with our differential equation for state 0 because we are looking specifically for the probability of having 0 users. Continuing with our calculation, we solve this simple differential equation using standard calculus techniques. This gives us an explicit exponential decay formula. This formula makes logical sense. The longer you wait, the closer the probability of 0 arrivals drops towards 0. Next, we substitute our specific real-world numbers into the exponent, an arrival rate of 4 and a time of 0.5 minutes. Now we just simplify the math to get our final answer. Multiplying 4 by 0.5 gives us exactly 2, so our exponent becomes negative 2. Evaluating e to the power of negative 2 on a standard scientific calculator gives us approximately 0.1353. This means there is a 13.53% chance that absolutely no users will connect to the network during those first 30 seconds. It also means there is an 86% chance someone does connect. Now that we have successfully used the formula, let us understand exactly where it comes from conceptually. To find the probability of having exactly n individuals at a future time, we look at a microscopic step forward in time, which we call delta t. There are only 2 realistic ways to end up with n individuals at this slightly later time. Either we already had n individuals and absolutely 0 births happened, or we had 1 less individual and exactly 1 birth happened during that tiny time gap. We multiply the starting probabilities by the chance of these events occurring. Continuing our derivation, we add the probabilities of those two distinct cases together to get the total probability for the new time. Next, we want to turn this into an equation that shows a rate of change, which is the foundation of a differential equation. To do this, we subtract the original probability from both sides of our equation. This isolates the change in probability on the left side, while the right side shows the balance of probabilities shifting between the states. The positive term represents gaining probability from below, and the negative term represents losing it to the state above. This sets us up perfectly for the final calculus step. For our final steps in this proof, we divide the entire equation by that tiny time gap delta t. This rearrangement gives us the average rate of change over that small period on the left side. Finally, we take the mathematical limit as the time gap shrinks down to exactly 0. In calculus, taking the limit of this fraction as the bottom goes to 0 transforms our average rate of change into an exact, instantaneous derivative with respect to time. And there we have it. We have successfully derived the fundamental differential equation for the pure birth process. So, we have proven how the general model works. This brings us to a very famous special case known as the Yule process. Imagine a single biological cell in a petri dish that divides into two. Now both can divide, making the next division happen faster. In the Yule process, the overall birth rate is directly proportional to the current population size. Every new member immediately starts contributing to the growth, creating an explosive population model. Because the birth rate follows such a strict proportional rule, we can solve the differential equations we just derived to get an explicit formula. This formula calculates the exact probability of having n individuals at time t, assuming we started with exactly one individual at time 0. The term e to the negative lambda t represents the chance that the original ancestor has not given birth yet. As time increases, this probability shrinks, and the system shifts toward larger and larger population sizes. This creates a geometric distribution pattern. Let us see this explosive growth formula in action. Suppose a rare bacteria colony follows a Yule process. It starts with exactly one bacterium, and the individual division rate is 0.5 divisions per hour. We want to find the exact probability that the colony has grown to exactly 3 bacteria after 2 hours. Since we start with one individual, we will use our explicit solution formula. Continuing with our calculation, we substitute our known values into the formula. We plug in 3 for the target population n, 0.5 for the individual birth rate lambda, and 2 for the elapsed time t. Next, we simplify the exponents. Multiplying the rate and time gives us exactly 1. The exponent for the second term becomes 2. This clears out the variables and leaves us with pure numbers. For the final steps, we evaluate e to the power of -1, which is approximately 0.3679. We substitute this decimal into the equation. Subtracting it from 1 gives us 0.6321. We square that number and multiply it by the first term. The final result is approximately 0.147. This means there is a 14.7% chance the colony contains exactly 3 bacteria after 2 hours. We have covered a lot of ground today. To summarize, the pure birth process is a mathematical model of a one-way street where a population can only increase. By defining a state-dependent birth rate, we can use differential equations to track probabilities over time. We also explored the Yule process, which perfectly describes explosive proportional growth. Understanding these purely additive systems is your first crucial step before tackling more complex models where both births and deaths occur. Great job!